We've just got a couple more topics left in springs, and so we're going to get going with, I guess, the penultimate topic that we will deal with in springs. Today, the main new thing that we do here is going to be looking at the the phenomena of fatigue in springs. Okay, so that's kind of our main goal that is new. But we have one other goal along the way that I would like to show you here, and it is a similar kind of a task to what was done a couple of, well, I guess I did a video on it just a few days ago, where you have to do a design for springs based on continuous variables. And one of the things, those of you who've seen that video, you probably noticed that it takes a pretty hefty piece of software relative to what you have on your desk during an exam to complete that kind of a task. And so what I'm going to show you is a task that's similar but backed off a little bit. And it's backed off in the form of we actually know a few more of the variables that we need to optimize around for this particular question. And so we'll do that, and it's something that you can accomplish in a calculator that you have available to you on your exam. So those are kind of the two big new things that we want to talk through today. So a lot of you are in the process of trying to get this problem copied down. I'm going to continue to let you do that, but I'm going to back up for just a second. Most of you noticed that the problem that we're working on here is a valve spring. Some of you have experience in automotive kind of stuff, so you're familiar with an application that looks very similar to what I have shown up here for the picture. And so, we're going to try to design that valve spring for static use and then evaluate it after we've designed it for static use, evaluate it for its susceptibility to fatigue, and kind of figure out whether or not we think it will last forever using a couple of different criteria. I want to focus in on one thing, though, before we get into this problem, and that is this word right here. There's basically, when you look at material properties of spring materials with respect to fatigue, it almost doesn't matter how strong the material is. There's kind of just one big parameter that goes into knowing how resilient these things are to fatigue, and that is, it has to do with the surface treatment on the springs, okay? And the surface treatment that you can either decide to apply or not is called shot peening, okay? And I want to give you an idea of what shot peening is. This is a process that can be done on other materials as well, but it's very commonly done on these springs that are meant for fatigue applications. To shot peen something is basically to more or less, it's similar to sandblasting actually. It's you blast a piece of material, but instead of blasting it with sand, you blast it with small round metal balls, all right? And by blasting the surface of the material with these small round metal balls, what happens is the balls will bounce off of the surface, and when they do, it will leave a minuscule little dimple on the surface of the material. And you might think that's kind of strange that helps in terms of making these materials more resilient against fatigue. I want to describe to you at least a mental way of understanding why this is the case. When the balls come and they bounce off of the surface, what happens is they create a little bit of stretching of the surface of the material. Okay? And as a matter of fact, when they make that stretching, okay, it stretches that surface out. What happens when you do that over the entire surface, it makes what's almost like a case around the material that is being treated in this way. And that case winds up just a little bit bigger in diameter. We're not talking much, but a little tiny bit bigger in diameter, that case that goes around the outer surface of the material winds up wanting to be just a little bit bigger in diameter because it's been stretched by these little shots that come in and peen the surface of the material. Okay? And so what happens is this, since this wants to be, bigger diameter, all right? And what we're looking at with these circles are like the cross-section through the spring wire, right? And this little piece on the outside, let me kind of highlighted here, this little ring that goes around the outside piece of material, that much of it wants to get bigger in diameter, but it can't because there's material to the inside that is holding it in at the diameter it was originally. So it's like that, you've actually stretched out the material, and yet that material is being held in, right, by the fact that it's connected. So that kind of looks like this. The ring on the outside is being pulled in with this kind of distributed force around the outside because the yellow ring there basically wants to be bigger than it actually can be. Well, that basically happens, if that's being pulled inward, it means you're pulling this outward, like this, right? And so why is this important? Well, what it does is it creates a compressive residual stress in this little case of material that goes around the outside of the spring wire, right? So that little annular area, which is not very big, it's like a little ring shape, right? That much material that I've highlighted in yellow has now been compressed, and it's held in that compression based on the fact that it's kind of pulling on the center piece of material. So this is kind of an outer ring, okay? And it's pulling on the center, the bulk of the material. And so that's, I found these images online that kind of describe what this surface is like, and that's where this little curve comes from. It's basically saying that as you move away from the surface of the material, what you're doing is you have these compressive residual stresses, but this is at the surface, and you move inward toward the middle of the piece of material. You're saying that it's compressive right there at the surface, but then as you come into the center, it actually goes up into this tensile range. All right. So, well, why is this important? Okay, like this is what shot peening does. It actually creates this compressive residual stress just on the outer surface of the material. Why does that help? Okay, so think about what we know of the process of fatigue. All right, we go back to what we kind of studied a little bit back in chapter 6 of this text. Fatigue, as best we understand it, is caused by little cracks that exist in the material, little imperfections that are in the material that as you begin to load and unload and load and unload, those little cracks basically are stretched apart a little bit, and there's probably a little bit more failure that happens at the tip of these little micro cracks each time that you open it up, and each time that you close it again, it's almost probably a similar kind of a process to bending a paper clip till it breaks, but locally right at the tips of each of those cracks, right? And so what happens by building up this compressive stress tends to close cracks, right? So even as we stress this material in a repeated fashion, the fact that we've built up this compressive stress in the surface of the material tends to close those cracks, and it tends to make it less susceptible to this phenomena of fatigue. Okay, so that's, like I said, the primary place where this is seen is in the building of springs, but this is not an unknown process to building of other kinds of machine parts as well. You can build up compressive stress in the surface, and that can be helpful. All right, so let's get into this problem a little more now that we've discussed the kind of the concept of shot peening and how it develops this beneficial residual stress in the surface. So with this particular problem, we have a few parameters that are given, all right? So let me kind of go through those real quick. First of all, maybe due to the constraints where we are going to implement these valves, let's say that we have a mean coil diameter that we just specify at the outset, okay? We want that to be 1 1/4 inch mean coil diameter, all right? Squared and ground ends are fairly typical for applications like this, so we'll say that that's also what it has. We want for the preload on this spring to be 50 pounds, and we want for the maximum force to be 150 pounds. Let me give you at least a bit of a vision as to why these two numbers, I made them up for now, but why these might be numbers that would be important in the bigger design of something like a valve train, okay? you have to probably have some kind of a minimum force that is closing the valve, or else you may not actually succeed in getting the valve all the way closed, all right? And part of the issue here actually is the fact that the valve is not massless. So one of the things that can happen in especially engines that have high RPM, you can have something that's called valve float, all right? Valve float is basically where the cams that operate the valves stop, the mass of the whole valve train tends to keep the valve open instead of it following the profile of the cam, all right? So there's a reason why we would need to have some minimum forces perhaps in a valve spring like this so that you can prevent something like valve float, all right? So let's just say that we don't ever want to have any less than 50 pounds, but maybe we don't ever want to have more than 150 pounds, and maybe some reasonable rationale as to why that might be is that maybe if you have too much force in there, you might end up damaging your cam or something, all right? So I'm giving you reasonable reasons why these might be numbers that would come out of a larger design like this. And the reason I'm doing that is just I want you to get the idea that to have to design a machine part, you often have to start with certain things that you're saying, I'm not going to design these parameters, but I am going to design these other ones, all right? And so I'm just trying to make that feel a little bit more realistic. All right, so those are those things that we know right at the very beginning. We also know that we want to have a minimum lift of 0.9 inches, okay? So we want to be able to have a 0.9 inch difference between the valve being closed and the valve being open. All right, so having said all of these things, what we want to do is we want to design the spring. That involves finding the wire diameter, the number of coils, and the free length of the spring, and then and we'll do that based on static analysis. Then once we have the spring designed, we are going to use ASME elliptic criterion to check for infinite life, and after that, I'm going to show you a specific fatigue criterion called the Sines criterion. That this is basically really only applied to springs, the Sines criterion, but it's a different criterion that we can use just for this application. A few assumptions that we will use along the way. Instead of us trying to go into Chapter 6 and try to evaluate all of the parameters that would set up an endurance limit for this material, what we can do is instead that gives you some data in the text called Zimmerli. It's named after the guy who figured this stuff out. We can use this information to get those endurance limits rather than kind of the whole process that we use in Chapter 6. The other one that we will use, you might remember back when we looked at how you find a shearing yield strength from other information, you have to use basically a percentage, and one of them that it cites in there comes from this guy, Semenov. And then what we're going to do is we're going to relax a constraint that we have to use standard wire sizes. So we're going to say we get to design the wire diameter to whatever size we want, which makes it a continuous design task rather than a discrete design task, okay? We're going to use a factor of safety of 1.2, but we'll do that at the maximum required deflection rather than at solid length, okay? So that means we don't have this requirement to be solid safe. We also want to try to minimize the material usage, and we're going to set the fractional overrun to closure to 0.15 so that we can try to, by making that as small as possible, it tends to minimize the height of the spring and still stay within kind of some recommended ranges of how springs should be designed. All right, where do you want to start with all this? That was kind of a lot of setup, but this is what we need. These are the steps we need to do. So where do you want to start? Okay. Based on the information given to us, what's one thing we could find pretty quickly? Yeah, so based on the information that we're given, we know that for a lift of 0.9 inches, right, it's going to have a difference in the amount of force carried of how much? 100 pounds, right? And so we can very quickly say that K, the K value that we need, is just going to be equal to that 150 pounds minus 50 pounds over 0.9 inches. Okay? And if we actually punch that in, it gives us 111.11 pounds per inch. Okay? So that gets us a little ways. We should be able to use some information like that to help us in this design in some way. Here's the thing, though. Let's actually think about this a little bit more broadly. We have two major equations that we tend to use whenever we're designing these springs. One of them has to do with the spring constant, but the other one has to do with stress. So let's look at these two, these two values real quick. So the shearing stress that we end up having, and this is kind of a maximum shearing stress, right, is going to be equal to the Bergstresser factor multiplied by what? Okay, 8 times the force. Okay, and actually I'll say if this is the maximum overall stress that we're going to experience at any point in time, then that would be based on the maximum force that it's going to experience. Then what? Okay, the mean coil diameter, D, over pi d cubed. Okay, where the lowercase d, the wire diameter, is what's used in the denominator. Okay, and then the other equation that we typically use a good bit is what? The spring rate equation says what? Okay, wire diameter to the fourth, G over 8 mean coil diameter cubed and number of active coils. Okay, here's what I want you to see with these two equations, and this is, this will be helpful, I think, for you whenever you're doing design. There is a variable that shows up in one of these and not the other, right? That would be this number of active coils. It's interesting to note that the stress that is experienced is actually independent of the number of active coils. Okay, so we don't actually have to solve for that number of active coils just yet. We can actually go back the other way as well, and we can say this maximum force, right, doesn't appear over in the spring constant equation, right? And so I just want to point out that a lot of times the process of figuring out which equation to start with, a lot of it's about looking at the things that you know and trying to use those values first, those equations first, the things that contain those items that you know. And so for us, where do you think we should start? Probably start with the stress question, right? And what we actually want to do is we happen to know some information, or we can at least find some information about what the static strength is for this, right? So what we want to do for our design question is we want to set this maximum stress we're actually experiencing equal to the allowable stress, right? Well, how do I figure out the allowable stress? I'll just put it in as a variable for right now. We want to set this equal to S sub sy, but then probably not exactly S sub sy. What do I want to actually set it equal to? This is what I think causes yielding failure in shear. Okay. Someone suggests one of those percentages that we had used before. That's not really what I'm thinking of, because we use those percentages to go from ultimate strength to yielding strength, right? But the factor we need to include here is factor of safety. Okay, so this is the basic idea of what we want to do. Is we want to take the strength that we might be able to figure out for our material, and by setting it equal to the stress equation, we will then be able to go back and solve for a wire diameter. Okay, so I'm going to set up that equation here real quick. To find S sub sy, what do I do? Okay. Right, you have to take some percentage of the ultimate strength, but even the ultimate strength is something that we need to find, all right? And so to find that ultimate strength, we look at what kind of material we're dealing with. The material is this chrome silicon, okay? And so in table 10.4, you find chrome silicon wire, and it gives you some suggestions for an exponent and a constant value there that will allow you to solve for the ultimate stress or ultimate strength, okay? And so anyway, the A value it gives there is 202, and that'll yield a value in KSI. So I take 202, and the equation basically is that divided by the diameter of the wire, which we don't know, taken to the exponent of 0.108. Okay, and so this information that I just put right here to find ultimate strength in a normal orientation comes from table 10.4. Okay, but as a few of you mentioned, we need to multiply this by some percentage, because now that we have ultimate strength in a normal orientation, you multiply it by some percentage in order to figure out the yielding strength in a shearing orientation, all right? And that's where this little assumption, I pushed it down here, but the Samanov approximation for S sub sy is on the bottom of page 517. It's equation 1016, all right? And the percentage is basically 56% for if you're using that approximation, okay? Some of you probably got used to using a value here of 0.45. That is another alternative, all right? And I think I mentioned earlier on, you just have to, you know, read the problem carefully and see what it's asking you for, all right? So if you see that kind of keyword of that name, then it allows you to figure out that it's 0.56 that you should use right here. All right, but then what do we need to do? Okay. Yeah, so what I'm going to do with all this is I'm going to divide it by my factor of safety that we need at my maximum deflection, which is exactly what I'm dealing with here. And I wanted that to be 1.2. Okay, now I need to set this equal to, the very first term there is the Bergstresser factor. Well, how do I figure out Bergstresser factor? It's based on spring index, right? And spring index is the ratio of mean coil diameter to wire diameter. Okay, what is mean coil diameter? Okay, given at the very beginning 1.25 inches. So what I'm going to do is make a little expression here in terms of that, well, I won't make it in terms of the spring index. I'll actually go ahead and substitute in the diameter values for spring index into the Bergstresser factor equation. And so that'll give me 4c plus 2, which is basically 4 times 1.25 inches over wire diameter plus 2 over 4 times 1.25 inches, that's again the mean coil diameter, over wire diameter, minus 3. And so what I've done there is I've now put in a term for Bergstresser factor. All right, for the next step, I'll just put in 8 F max. Okay, what is F max? 150 pounds. We got to do something there. Okay, we probably need to convert it one direction or the other. The suggestion was, does that need to be in kips because of the left side of the equation, because of the fact that that's going to be in KSI? So yes, we do need to do a conversion on either one side or the other of this equation. So I'm not opposed to doing it on this side. May as well put it in there as, 1,000 pounds, right, is 1 kip. All right, and then we have our mean coil diameter again of 1.25 inches. And I take this and divide it by pi times my diameter cubed, my wire diameter cubed. All right, what do you notice here? We have an equation in one variable. It's a big mess, but it's an equation in one variable. And so that means that we should be able to solve it. Okay? And so I'm going to go ahead and punch this in. So what we have here is 202 over, here I'll put in my x value, but I'll take that to the 0.108. Okay? And this is all going to be divided by 1.2 and multiplied up here by 0.56. Okay? And this is all going to be equal to, all right, over here, let me do this as one big old fraction. Actually, I don't suppose I have to do that. I'm going to try it with two fractions. One of the tricky parts about this is when you have to enter this whole big thing, sometimes you run out of characters in your calculator. So try to be as compact as possible. So 4 times 1.25, I'll tell you what, I'll do it this way. 4 times 1.25 over x. Okay, and down here I'll do 4 times 1.25 over x. Okay, in the denominator I take this and I subtract 3. In the numerator I take that and add 2. Okay, so now take all of that and multiply it by another fraction, where I have 8 times 150 times 1.25, and then I divide all of this by 1,000 times pi. Am I going to make it? Times x. Almost made it. What can I do here? Yeah, here's what I'm going to do. Okay. Oops. All right. I'm going to take this 150 and do what? 0.150. That should do it, right? And then down here, I need to go ahead and put my cubed term on there.
Another thing is whenever you do the big bar for the divide by, that takes up more space than the slash.
Yeah, there can be some, the suggestion is sometimes using these fraction constructions rather than just putting in parentheses with a divide by sign. Sometimes that can take up more space. But anyway, you hit shift, solve for x, and pray. All right. Now, what are some of the things you can do to make this more likely to solve? Okay, you can maybe reduce stuff down. One of the things you can do is if you have some vague idea of what the D is going to be, right, the wire diameter, you can enter that as an initial guess. The other way that, you know, before the days of having a nice calculator like this, it wouldn't have been uncommon for someone to make a guess for the wire diameter with respect to finding something like the strength of the material and just plug in a strength of material, come up with the wire diameter, and then do an iterative technique from there. Because that's actually, the strength of the wire material doesn't change a lot relative to D, and so you can kind of eliminate that and do a more iterative approach. But anyway, we have these really nice calculators, and that ends up allowing us to solve for the diameter. In this case, it comes out to be 0.1708, all right, and that's in inches. Okay, and you noticed how long it took for my computer to crunch that. That's with the processor of my computer in that emulator, right? Your calculator is probably going to take longer. And so I'll just mention that. Don't get discouraged if you have to let it sit there for a bit of time and let it do its thing. It very often will solve, even if it takes a while. All right, so there is my wire diameter. What can I do with that to completely design the rest of my spring? Okay, now that I know the wire diameter, I can stick it into the equation for K, and you might notice that the only thing I don't know in that equation for K is my number of active coils. All right, so that's good. We can go ahead and put that in. 111.11 pounds per inch is going to be equal to 0.1708 inches raised to the fourth. Okay, what kind of a G value should I use here? Okay, you might remember that the modulus of rigidity is something that varies with wire diameter. So we need to look up a chrome silicon wire in table 10.5, and it looks like for that particular wire it doesn't vary, right? So we just use the value that's given there, 11.2 MPSI. So 11.2 times 10 to the 6th PSI. Okay. In the denominator, I have 8 times d cubed. All right, that again is 1.25 inches cubed. And then lastly, we have that n sub a, which is what we're trying to solve for. Which if we punch those things in, it comes out to be 5.49 coils. All right. So far so good. What we've now done is we have accounted for D and for my number of coils N. By the way, how many total coils would this be if I needed to know that? Okay, 7.49 coils. I don't know that that comes into this question per se, but in case you're wondering, that's you'd add 2 based on table 10.1. All right, but the last thing that we need to know here is the free length, L sub 0. Okay, so to find L sub 0, let's go back to that table 10.1 in order to figure out what my solid length is. Okay, so solid length is just going to be equal to the wire diameter times the total number of coils. So the wire diameter is 0.1708 inches, and the total number of coils, okay, this is based on table 10.1, total number of coils is 7.49. All right, and that gives me a solid length of 1.279 inches. All right, so 1.279 inches there. How do I use that to get my solid force? Okay, so I would actually maybe say it this way. Solid force, I can get that from table or from equation 1017 because it's 1 plus the fractional overrun to closure times my maximum force. Okay, so this comes from equation 1017. All right, and we actually happen to know that we want for fractional overrun to closure to be 0.15. and we want for my maximum force to be 150 pounds. Okay, so this allows me to directly solve for solid force. It ends up being 172.5 pounds. Okay. And here's where we find our free length. We go back to understanding Hooke's law and the fact that if we know force, then we can use spring constant to find a delta, right? So what I can say there is Fs is equal to K, spring constant K, delta S, which is equal to K times the free length minus the solid length. Okay, and so if we actually punch in the values here, this tells us that 172.5 pounds is equal to 111.11 pound per inch times free length minus solid length, and solid length was 1.279 inches. Okay, and so that lets me now set the free length, which is going to be 2.8315 inches. All right, and now we have enough information for us to actually build the spring, right? We know the free length, we know the wire diameter and the mean coil diameter, and the number of coils, right? So that provides all the information that we would need to wind this particular spring. All right, that was basically all of that stuff that I just showed you is showing you a design around a continuous or continuous variables, right? That's one of the points that I had for today. What I'm doing now is kind of transitioning into the fatigue question, all right? So I'll tell you what, I'm going to go back up to the original and then push all this stuff down, and we'll start answering the question about whether or not this spring is going to be okay for infinite life, all right? So here's where I want to start with that. You might remember that we had a few plots that described kind of our failure locus plots for fatigue. And you may remember that they looked something like this, right? They were on a set of axes that involved mid-range and alternating, kind of mid-range alternating stress, as well as endurance limit and some sort of a static strength value for a piece of material. All right, and for all of these things, all of these different curves, or pretty much all of them, most of them, kind of they end up on this vertical axis at a particular value. What value is that? Okay, so whether we're talking about there being an ASME elliptic, which kind of is shaped like this, or how's Gerber shaped? Okay, Gerber is shaped maybe a little bit more like a parabola, something like that. Or how's Goodman shaped? Okay, Goodman would have been a straight line from this point down to that point, okay? But then it tends to get cut off with a, kind of the yielding criterion, which might be a 45-degree line that cuts off the end of the Goodman line. So anyway, I'm showing you there's a bunch of these different kinds of yielding criteria where this is alternating and this is mid-range. stresses. Okay. Now, here's the thing. We have a strange form of information that comes to us in terms of knowing the strength of a spring material against fatigue. Okay, and that's where this idea of Zimmerli data comes in. On page 528, there's two equations given, equation 1028 and 1029. Okay, and it basically says that this guy Zimmerli tested a bunch of springs and more or less found out that the shearing strength, the alternating and mid-range components of shearing strength for unpeened springs were more or less constant. All right, and that the mid-range and alternating shearing stress for peened materials were also more or less constant. All right, but they are not set at either end of the failure criteria, locus. Okay, so what we basically have here is that we are given 1 point on any one of these curves. All right, and by picking which of the curves, which of the types of failure criteria we're going to use, we can do something like find a point up here where the curves intersect with the alternating axis. I'm going to show you that for the ASME elliptic criterion. Okay, so let me give you this. This is the equation of the ASME elliptic curve. You take the alternating stress and you divide it by the shearing endurance limit. And that is going to be squared. You add to this the mid-range shearing stress, and you divide this by S sub Sy, which is the yielding strength in shear for that material. Okay, and this is going to be set equal to 1 over the factor of safety squared. Okay, if you're curious where I got that, it comes out of Chapter 6. There are a number of expressions that give you ASME elliptic curves, and so that's where I got that equation. All right. Well, so, what do we do with this? Well, what we do is we understand that what we can do is we can plug in the Zimmerli data into my mid-range and alternating stress values and set it equal to 1, because these curves that we see here are assuming that that's kind of where failure, where infinite life stops happening, right? And we say where it stops being infinite life, that's where we're going to assume that we have failure. And so that, the actual curve for any one of these implies a factor of safety of 1. Okay? So what I'm saying is we basically plug in Zimmerli data into here, and we basically say S sub SA over S sub SE squared plus S sub SM over S sub SY squared is equal to 1. So why is this helpful? Because we basically just plugged in the Zimmerli data what out of these equations for a standard problem like the one that we're working right now, what out of these equations don't we know yet? Yeah, the endurance limit, right? So we were just given, based on these equations, the Zimmerli data, so we have those as long as we know whether or not it's peened or unpeened, right? And we also have already calculated S sub Sy, right, based on the Samanov percentage. So the only thing that we don't know now is the S sub Se, and now we can calculate that based on everything else that we know. And kind of graphically what we are finding by doing this is we're finding how high is this intersection point right here on this axis. Okay, that's kind of graphically what we're doing by calculating that. So let's go ahead and do it. Okay, we have a peened spring. So therefore, I look here at equation 1029, and it says S sub SA is 57.5 KSI. 57.5. Okay, what I'm trying to find is S sub SE. S sub SM is 77.5 KSI. Okay. And this gets divided by S sub SY. Okay, and S sub SY from earlier, did we ever find that all by itself? I guess we didn't. All right, let's go ahead and calculate that. The stuff that we had up here in the numerator, right, if I calculate all of that, that gives me S sub SY. So I'll go ahead and punch that in, I suppose. So I already have D stored into X, and so basically I'll take 202 times 0.56 and divide by what I have stored in X. Okay. Yeah, thank you. Got to raise that to the exponent. Exponent of 0.108. That's better. So that gives me 136.9 KSI. Okay, and if we punch this in, we end up getting a endurance limit in shear of 69.75 KSI. All right, so what? Why does that help us? Right, so for us, we have maybe different mid-range and alternating stresses, but when we plug those in, or when we find them, those mid-range and alternating stresses, we can plug them in to our ASME elliptic equation with our factor of safety, or, in our case, we just want to know, will it last forever or not? So what does that mean? Do we need a factor of safety in that case? Yeah, a factor of safety of 1 is that threshold where we expect whether or not it will last forever or not. So that's kind of the next steps. So how do we do that? Okay, I need to find my max and min shearing stresses, okay, so that I can then find mid-range and alternating shearing forces. Well, this includes the Bergstresser factor. So 4 times 1.25 inches over 0.1708 inches plus 2 over 4 times 1.25 inches over 0.1708 inches minus 3. All this times 8 times 150 pounds times 1.25 inches. Okay, divided by pi times d cubed, where lowercase d is the wire diameter, and again, that's cubed. All right, now what if I want this to come out in KSI? Okay, yeah, I'd probably want to divide that 150 pounds by 1,000. So 1,000 pounds per kip. Okay, so once we do all of those calculations, my maximum stress here turns out to be 114 KSI. All right. Now when I find my minimum stress, which is, at the other end of the scale, right, it's going to vary between 50 pounds and 150 pounds. So my minimum stress is where I've got the 50 pounds in the spring, and that's really the only thing that changes. Okay, all I do is I come in here and make that 50 pounds instead of 150 pounds. And that creates my minimum stress. All right. And I've got that at 38 KSI. All right, so then what? Okay, I need mid-range and alternating, right? So mid-range stress is going to be equal to the average of these two, 114 KSI plus 38 KSI over 2. This ends up giving me 76 KSI. And my alternating stress is just 114 KSI minus 38 KSI over 2. Okay, which, by the way, well, I guess they don't have them in there in exactly that form, but they have F sub A and F sub M, so it just basically does it instead of with respect to stresses, it does it with respect to forces, but standard equations that we use to find mid-range and alternating. This ends up giving me 38 KSI. Okay, so those are the values that I will use in the ASME elliptic equation, which you're certainly welcome to use the form of it that we've a lot of time used, where it kind of has the radical all built into it and everything. You might remember that expression of it back from the table in chapter 6, but that's just a rearranged version of the same one that we wrote up here a moment ago. So what we'll do is we'll just say 38, so 1 being my factor of safety. I'll tell you what, rather than just setting it equal to 1 and doing an is this greater than or not, we actually can calculate a factor of safety here. Okay, fatigue factor of safety. And this is going to be equal to 38 KSI as my alternating stress over my endurance limit. The endurance limit that I had said a second ago was 69.75 KSI. This squared plus 76 KSI as my mid-range shearing stress, and that would be divided by the 136.9 KSI that I found a moment ago for my yielding strength in shear. Okay, and if we solve this for n sub f, it ends up giving me 1.286. So what's our conclusion? At least based on this failure criterion, we expect it will last forever because my factor of safety is greater than 1. All right, so that is for the ASME elliptic criterion. Okay, now we do have one other criterion we can use, and it is specifically for the question of springs. It is called the signs criterion. Okay. The science criterion is based on the idea that according to test data, when they actually go to test these springs, their failure, kind of what they exhibit in terms of their failure behavior is actually less dependent on the mid-range stress than most of these failure criterion seem to predict. All right. In other words, it seems to be a function more of just the alternating component than of the mid-range component. And so what they do with the science criterion is they basically just say, we're going to ignore the mid-range criterion, or the mid-range value of stress, and just use the science criterion. So essentially, if you wanted to make a sketch of what that would look like on a chart like this, let's say that, I don't know exactly where our point was, but let's say our Zimmerli data created a point that was somewhere in here, just for instance. And we came up with this, little chart like this. What the science criterion says this looks like is much more simple than that. Science criterion says that this basically works like a horizontal line through that point, which is a lot easier, right? And so it makes it, really simple for us to calculate a factor of safety. You basically just say, what is the value of alternating stress that you should be able to carry, which is, according to Zimmerli data, 57.5 KSI, and you divide it by the amount of alternating stress that you are actually applying to the spring, which was 38 KSI. And this says that we actually have a factor of safety, according to that criterion, more like 1.51. Okay. So science criterion, they don't have equations that are sort of boiled out, at least not up here in the main part of the text for that. It describes it. It says, kind of in the paragraph at the bottom of 528, page 528, says springs are free of notches and surfaces are often very smooth. Oh, it actually kind of references the part right before that. An extended study of available literature regarding torsional fatigue found that for polished, notch-free cylindrical specimens subject to torsional shear stress, the maximum alternating stress that may be imposed without causing failure is constant and independent of the mean stress in the cycle. All right, and it's basically saying springs exhibit those, typically, many times anyway, they exhibit those characteristics, and so science failure criterion is often something that's okay to use for that purpose. So, I believe if you look in some of the example problems that they have in the text, they actually do, I think they actually use the science criterion in that example problem right after this section. So if you want to see that, but it's the same thing I did basically. All right. Any questions before we wrap this up? All right. Well, then I will see you guys on Friday.